All right, 9.2, like I said, a lot of the things that we need to do here were done in 9.1. I crammed a lot of information in there. .2 is on testing the population proportion. So we're going to be doing proportions, which is exactly what we did in 9.1. And 9.3 we'll be doing testing for the population mean, and that's going to be a new, slightly new thing, but the same process overall. We're going to go straight to an example. A pharmaceutical with the EU. All right, if I misspelled it, just ignore that. Claims 8% of subjects experience side effects as a result of their new medication. If we want to test this, we just take a sample of their patients taking that new medication, figure out who's experiencing side effects compared to that 8%. Suppose in a sample of 65 subjects taking that new medication, but I'm not going to write that, 15.4% experienced side effects. That is higher than their claim, but it could be random variation. It could just be the randomness of this random sample of 65 subjects that just happen to get a lot of sensitive people, or sensitive to medication, that is. Okay. Does this provide, oh, I got no space to do my work. Does this provide sufficient evidence no, we're changing it. So I kept it simple in the beginning, just sticking with 5%, which is usually the customary standard. But they do want you to be able to apply the same sort of principle to different significance levels at the 1% significance level this time. The common ones, and we are going to stick to the common ones, are 10%, 5%, and 1%. Over here we do 1% significance level. That the percentage of patients experiencing side effects is more than 8%, greater than their claim. Okay, so they're claiming 8%. We took a sample on 15.4% experienced side effects. And is this sufficient evidence at specifically the 1% significance level that they are understating the rate of side effects that is greater than their claim? So they'd want to downplay their side effects, and if they're shady, they may have lied or manipulated things. And anyway, the basic way to test out whether they're lying is to take a sample of their subjects and find out what percent is experiencing side effects. It's better to take a bigger sample size, but sometimes you don't have that luxury. Anyway, the question is there. The process is what we did in 9.1. We'll go through the process again. So they didn't they didn't ask part A, part B, part C, part D, but it is the same 4 things, which I'm going to cram here. If that's in frame, oh, it's in frame, but it's got the glare. Let's see. No, that made it worse. Fine, I'm going to cram it down here. I'll cram it in our race as I go. All right, 1. State. You don't have to write this down every time. I'm reminding you of the steps, and I'm going to abbreviate because I don't got much room. All right, we're going to state the null unalternative. This is helpful. It may seem like a minor thing you could skip. You probably could, in all honesty, but it is helpful, especially when we talk about type 1, type 2 errors, which we are. So this is where I'm going to really get into that now when we get to the end of this, when we draw our conclusions. So it'll be helpful to have this on the board. Oh, we got to decide, is it proportions or means? Are you talking about percentages of things or averages of things? They're talking about percentages of patients experiencing side effects. So it is a proportion test. You will have to make that distinction when you get to your exam. So be aware, there's one for proportions, there's one for means. We are doing proportions. Our null is what they claim. They claim 8%. Last time in 9.1, we had a company, another type of company, claiming that 80% of their customers were satisfied, and so we used 0.80. That was 80%. This is 8%, not 80, so it's 0.08, not 0.8. Be careful about your conversion to decimals. Your alternative involves P, and it involves 0.08, 8%, and it's just a matter of what symbol based on what we're testing. We're testing to see if it's more than their claim. So we're looking at a greater than, that's a right tail test. That'll be relevant once we get to the p-value step. 2. Calculate the test statistic. All right, let me summarize what we need for it. Oh, hold on. You will see under hypothesis testing the Z statistic and you will see the T statistic, both listed under hypothesis testing. So you'll see these two things available to you, the two test statistics that we're using in chapter 9. There's going to be one more in chapter 10, but for now you have to make a distinction. The one with P's, hats, and P's are obviously for proportions. The one for X bar and mu's is for means. So we're doing the Z one. Look at what we need. I'm going to start writing it down here. I need a P hat. I need a P. I need a Q. I need an N. That's it. Okay. P hat is the sample proportion. It's the percentage of the subjects, the 65, that experience side effects. Now, in the last example, in 9.1, I told you how many out of the 65, and you have to divide. You have to do P hat is equal to something over 65. Now, they didn't give us a count. They gave us a percent of that sample that experienced side effects, meaning you don't have to do this. They did it for you. Don't try and cram 50.4 divided by 60. Don't convert it to a decimal. Well, don't put a decimal form up here. We don't need to do that. They already did it for us and told us the answer P hat is 0.154. So be aware, sometimes they just give you P hat and you don't have to do that one step of dividing. So here, the percentage, the proportion of the sample that experienced side effects is literally 0.154. Again, they already computed P hat for us. They gave it to us in percent form. We just got to move that decimal to get decimal form. All right, P is the population proportion that experienced side effects, which we're testing. So we're not sure what it is, but this whole process of hypothesis testing goes with assuming the null is true. So we're going to use P is equal to 0.08 and then base Q on that. So we assume the null is true until we have evidence otherwise. So for now, we're going to be using 0.08 as our P, the percentage of all their patients that experience side effects. This is the percentage of the sample that experience side effects. Make sure you understand the distinction between the sample proportion and the population proportion. Q is 1 minus P, not 1 minus P hat, 1 minus P. That's going to be 0.92. And N is 65. That's why they have to give it to you. Even though they give you P hat, you need N. You don't need to know how many subjects experience side effects as long as you get the percentage. But you need to know N, the number in your sample. All right, I'm going to use a space, not too much glare, but all right, following that formula right there, 0.154. The order on top is important. Make sure you don't put 0.08 and then 0.154. Don't put P minus P hat. It's P hat minus P. And on the bottom, don't mistake those. Those aren't P hats or Q hats. Those are P and Q divided by N. the computation isn't as bad. It'll be, we have to really worry about the T1 when we get to it. This one's not too bad, but you definitely want to make sure you remember parentheses on top. So I do recommend you do it one step so you don't get rounding errors that can make your answers slightly off. And the more steps you take, the more rounding you do along the way, the bigger your errors, and to get to the point where it does actually make a difference. So try to do this computation in one step. Parentheses around the top, divide by one big square root. Again, everybody's calculator is different on how they handle the square roots, and just make sure all of that's crammed under there. And again, I try to minimize the use of parentheses within here, even though I write it on the board that way. What happened? 65. Okay, I got 2.199. This is a z-score. So if you want to follow the convention, the guidelines for rounding, z-scores rounded to 3 places. So 2.199, I'm going to start erasing the problem. Make a note of this, so 1% significance level. I'll make a note of it, but on your homework you obviously have the paper that you can refer back to. I'm limited on board space, so I just have to stick that in our memory. Okay, so if I'm going in steps, that's my answer for stating the null alternative. Again, there was no part A, part B, part C, but if there were, that'd be the first step. That's the result of the second step. That is your test statistic. And the next step is our p-value. And the p-value is based on the distribution of the statistic. It is a z. What distribution does that have? Well, z's have the standard normal distribution in general. That's what the z convention is. It also is normal, standard normal, because it says it right there. So this statistic has this distribution, meaning any probabilities we want to get will be off of that N01. And I'm not going to mark off all the tick marks. I'm just going to clutter up my picture. But I do want to note that as we do this test, they claim 8% experience side effects. And if we get a sample of 65, or it doesn't matter what, and the 8% of our sample exactly what they claim, don't write this down because this is not relevant to the problem. It's just hypothetically, if we get 8%, we get a z-score dead center. If we get a p-hat that is less than that, let's say 0.06, that means 6% of our sample experience side effects. We're definitely not going to reject, we're definitely believe them, because that's evidence that corroborates their claim. That's even less than their claim. The p-value would be this entire right thing. You don't just go to the closest tail, you go based on this. So if 6% of our sample had side effects, our p-value is the right tail, because it's greater than, it's a right tail test. And we would get a very big p-value, and we would definitely not reject. If you get a p-hat is equal to 0.154, let's say, or sorry, yeah, I shouldn't be drawing these p-hats on here. Well, okay, it's fine. These are actually z-scores here, but okay. Sorry, I'm fine. P-hat 0.6 will end up with a z-score there. Your p-value is going to be that way. But p-hat of 0.08 means you get a z-score of exactly 0. It's going to be p-value going that way. And if you get a p-hat of 0.154, you're going to get a z-score that's on the right. How far to the right? Well, we just figured it out. That's the z-score that we get from a p-hat of 0.154. So the value that's actually on here is the z-score of that p-hat value. So that z-score came from a p-hat of 0.154. So again, just to clarify, since I kind of got a little confused there, or messed up myself, if you get a p-hat that's exactly 0.08, you will get a computation that gets you the z-score of exactly 0 right there. If you get a p-hat of 0.06, that's actually less than their claim, you get a z-score that's on this side. And if you get a p-hat that's greater than their claim, 15.4% greater than their 0.08, you get a z-score that's to the right. And so the p-value that we're looking for is that probability in the right tail, because we're doing a right tail test. So our p-value is going to be based on us doing a normal CDF problem using the z-score, not the p-hat, because we're using the standard normal curve and we're using our test statistic a z-score on your standard normal curve of 2.199 to infinity, 10 to the 99. And if you have to put parameters in, make sure you're using 0 and 1 and not anything else, because it is standard normal, because it is a z-score that we compute. All right, let's do that. What did I just say? 2.199, 10 to the 99, 0 and 1. Okay, and I got a p-value. Let me label that. P-value is equal to 0.0139. The convention for that's a probability, and the convention for probabilities was 4 places, but if you don't, you can go to 3 places because we only need to be able to compare it to the significance level. So for in this case, we make an exception, sort of. 3 places is just fine. So I'll be going to 3 places for my p-value. All right. That is not 14%, that is 1.4%. Be aware of that, because our next step is to draw our conclusion. I gotta label this. This is the p-value. And here is our, no, it's not 3. Damn it. I've been doing lectures all day with my other class, so. Conclusions. Conclusion. Do we believe them or not? Are we rejecting the null or are we not rejecting it? The null is that it's 8%. What do we think? Again, 15.4% is higher than their claim, but is it enough evidence? What we do is we take our p-value, right over there, we compare it to the significance level alpha. It's been erased from the board, but if you recall, it was 1%, not 0.1, 0.01. 1% significance level. Our p-value is 0.014. Again, don't mistake that for 14%. That is 1.4%. Which one is bigger? That one is slightly bigger. And that means that's not enough evidence. Small p-values are evidence that something's wrong. Small p-values are what you need to reject their null, their claim. You believe their claim until you have strong evidence otherwise, and that strong evidence is in the form of a small p-value. This is pretty small, but not small, not enough, not below the cutoff. So our conclusion here is we do not reject. I want to emphasize, we do not reject at the 1% level. You don't have to write that as part of your answer. I'm only mentioning it because I want you to know that you would have a different conclusion for a different significance level. This is a standard you're going for, and this is a high standard. We do not reject at the 1% significance level. So you do not have sufficient evidence. Let me write that. You can just write do not reject or reject, but if you want to understand you do not have sufficient evidence to sue this pharmaceutical company, at least not at the 1% standard. What am I writing? Do not have sufficient evidence. Okay, so you don't have enough evidence to convict them in a court of law, so you're not going to sue them. All right, where am I at? I'm going to erase all this. Oh, I need that. I'll come back to it. I'm going to make a note. I kind of just mentioned it now, but let me summarize it for your notes. Is a higher standard. Meaning you need stronger evidence to meet that standard. 1% is a higher standard of evidence than 5%. From the ones that we are going to do, 1% is the high standard, 10% is the lowest, loosest standard, and 5% is medium-ish, although 5% is the one that's most commonly used. All right. We did that before. The only thing that was new was it was a right tail test. This is the first time us doing that, but it just means that you're doing literally the right tail on your probability distribution for your p-value step. I'm going to erase. But we're not done with this problem because I have some follow-up questions to this. couple of things I need to carry over that I'm going to write down. Our null and alternative, I'm going to refer to that. Our computations came up with a conclusion. I'll write out more than I need. 0.014, 0.01, it was greater than, so we did not reject. And what that means is we are giving the company the benefit of the doubt, and we essentially believe them. We did not find enough evidence to call them out as lying or false advertising. So this means we believe the company. It wasn't enough evidence. Okay, some follow-up questions. Oh no, my computer went to sleep. Suppose, now when you make your conclusion, you never really know whether it was a correct decision or not. You can't really tell if the company is lying or telling the truth unless you break into their headquarters and photocopy some of their private documents. But for us, we're going to do a hypothetical. Suppose we do find out whether or not the company was lying or false advertising. So here's our hypothetical. Suppose 8% of patients suffered side effects. As claimed. What type of error occurred in our analysis? I'm just going to go what type of error occurred, but basically when we did our analysis, when we came to this conclusion, did we make an error, and if we did, what type? I'm going to leave space for our answer and our work. I'm just going to give you a little bit of organization, not so much computation. And now I'm going to have a separate follow-up question that's similar. Suppose the true percentage of patients experiencing side effects was greater than 8%, greater than the claim. What type of error occurred? And I'll leave some space for our analysis there. Okay, so our answers here are going to be based on two things. What this is describing, whether this is saying the company was telling the truth or not, but also based on our decision. So it's basically what type of error occurred with our decision, our conclusion here. So this is this is going to be part of how we figure out the answer. Another important thing is that you know your errors, and we went over this in 9.1. And you got a table, and so if H was true and you rejected, you made a type 1 error. If H was false and you did not reject, you should have rejected, but you didn't, you made a type 2 error. But there are scenarios where you made the correct decision. If H was false, the company was lying, and you rejected their claim, you made the correct decision. You called them out correctly. If H was true, the company was telling the truth, and you chose not to reject their claim, meaning you would kind of believe them, you gave them the benefit of the doubt, that's the correct decision. You gave the benefit of the doubt to an honest company. All right, so basically to figure out which one you're doing, you need to know what column and what row you're looking at. And that's what I want to emphasize on organizing this. I'm going to put that back up in a little bit, but we'll refer to that once we're ready to pick the one that applies. This is going to be relevant for both of them. Do not reject. So our answers here should definitely be from the bottom row, because we definitely did not reject, and we either made a type 2 error or no error, depending on if H was true or H was false. So we're looking at these two. All right. So the main thing is we first decide whether HO is true or false. This is a question as of now. And it's based on the description here, based on this scenario that's described in the suppose this hypothetical scenario of 8% of the patients suffered side effects as claimed. Now, all of this is referring to the null, whether the null is true or the null is false. That's why I wrote down the null right there. The company, that's their company's claim. So that's your null. Is this hypothetical saying HO is true or HO is false? HO is saying that he had 8% side effects. This is saying suppose that 8% was correct as claimed. This is saying HO is true. There's a race of false, but that was a question that I've decided that this hypothetical is saying that HO is true. What did we do with our conclusion after we gathered evidence and did our analysis? We did not reject. We did not reject something that was true. Let me write that down. So I recommend you kind of organize your work. Specifically, is HO is true or false in this scenario? And then did we reject or not reject in our previous work? Now, I can grab that chart and I can pick it out on the chart what our answer is. But I'm fine with that because I'll be honest with you, even if you were taking a test in class, you would have on your formula sheet this whole table. And the reason is because the distinction between type 2 and type 1, I don't remember which one is which, to be honest with you, so I would need a table to look it up. And I'm going to, for sure. But I do want you to be able to tell whether an error was made or not. Not necessarily the type, because again, type 1 and type 2, those terms are very non-descriptive. But definitely, can we look at this and say, was that the correct decision or was it the wrong decision? The company was telling the truth. We did not reject their claim, meaning we believed them. We kind of accepted it. We never say we accept it, but let's say we accepted it. We accepted their claim and their claim was true. Was that an error? No, that's a correct decision. So without even looking at that table below, I can definitely say we made the correct decision there. So correct decision, no error if you're writing it for homework, but on the exam it would be multiple choice. So you just pick either type 1, type 2, or no error. And this one is no error. That's the correct decision there. We can verify that right here. HO is true. We did not reject. That's that one right there. That confirms it was no error. Okay, so that's the idea. We just got to kind of organize and sort through the thoughts described in this scenario. So let's look at this next one. It's referring to the same decision here, so it's still do not reject, but let's make sure we do the first thing. Is this saying HO is true or HO is false? Based on this suppose scenario. Suppose the true percentage of patients experiencing side effects was greater than their 8%. The null is it's 8%. The alternative is greater than 8%. So that means this is saying the alternative is true, but the null is false. It's not 8%. Suppose it's higher than that. So this scenario right here, greater than 8%, is saying HO is false. That means the company was lying. So suppose the company was lying. What type of error did we make? Well, we did not reject it, meaning we believed them. We let them off the hook and they were lying all along. Is that an error or is that the correct decision? They lied, we didn't call them out. It was definitely an error. What type? I don't know, I gotta look it up, so I don't know my errors. Definitely one of the two errors. Do not reject, which was false. Right there, type 2. And we are done. That's how you're going to be analyzing some errors. Okay. I'm going to follow up with this. So, does the previous data where 15.4% of the 65 experienced side effects provide sufficient evidence at the 10% significance level. To reject the company's claim. No, I can't just write that. To conclude, their percentage of patients experiencing side effects is greater than 8%. I have to specify it's greater than because you could change up whether it's a left tail, right tail, or two-tailed, so I still need to emphasize that. Okay, so this is basically redoing the same process. There's a lot of homework problems like this where I basically reformulate the question so that you have to adjust. I don't want you necessarily having to do the entire thing again. Those are designed for you to think about what stays the same and what changes with this new situation. What's different about this? We're still doing greater than, so I can go ahead and do my HO is, I'm going to write it down because I'm going to refer to it later. HO is still 0.08 and the alternative is still testing this greater than. Sometimes the follow-up question changes that and you test if it's less than or different from. But this is still a right-tailed test. That's not different. Our data is still from the same sample. Same sample size, same p-hat. We're still using the same p and q, so your z statistic is still going to be 2.199. Where'd it go? 2.199. Your p-value, it's still a right-tailed test, so that's still going to be the same p-value. I'm just drawing it out, but if you realize all this is the same up to this point, you don't have to keep drawing it out. 2.199 is my z-score. I'm still doing a right-tailed test. Normal CDF, the same computation, and give me a 0.014 is my p-value. What's different is when I do my conclusion, it's a different standard. Last time it was 1%, this time it's 10%. Everything's the same except we're using a looser standard of evidence. And now using this looser standard, do we have sufficient evidence to reject their claim? Let's see. So the last step is the only thing, the significance level. And so you wouldn't have to do any other computations if you recognize everything's the same except your comparison at the end to a new alpha. 10% is 0.10, 1% is 0.01. You don't have to write the percent. I'm writing it mainly so people that aren't really good at looking at a decimal and interpreting it immediately in their head as a percent. Let me write it out for you, but you kind of got to develop that, hopefully. P-value was 0, where'd it go? 0.014. And that's 1.4%. And that is definitely less than that new significance level. Again, small p-values are evidence. That's small. It wasn't small enough to meet the 1% standard for us to sue them, but this looser standard where we're ready to sue them at the drop of a hat, yes, that's sufficient evidence for us to sue them. We are rejecting their claim here. We think the percentage is higher. Okay, so we're rejecting their claim. We think the company's lying about or understating their rate of side effects. Okay, so that's answering that question, but I wanted to do that so I can do some follow-up questions. And I'm going to cram them over here. Let me just box off a little room here. It's going to be the same questions as I did for the errors. I literally worded it the same way, but I'm going to condense it down. Suppose 8% suffer side effects. What type of error occurred? Am I writing too small? You're good. Second follow-up question. Suppose more than 8% suffer side effects. what type of error occurred? Remember that our error types depends on what this scenario is describing as related to whether HO is true or HO is false, whether the company was telling the truth all along or not. It's also based on our conclusion, our decision on whether to reject or not reject. And that changed from last time using the lower standards. So we've got to redo this analysis, even though they're literally the same questions as we had for the previous test. Okay, let's go through it again. First step, know what HO is. Think about what it represents. That's a company claiming that 8% of their patients suffer side effects. What is this saying about HO? Is it true or false? Suppose 8% suffer side effects, exactly as the company claims. This is saying suppose the company is telling the truth and our HO is true. What do? We reject it. We tried to sue them over this. Before I grab that thing, is that the correct decision or not? They were telling the truth. HO is true. We reject their claim. We called them liars. That is definitely an error. That was a wrong decision. HO is true. We rejected. Type 1. Next follow-up question. Suppose more than 8% suffer side effects. The null. We're always referring to the null. The null is that it's 8%. We can look at the alternative, but basically we're looking for whether HO is true or not. If it's over 8%, that means the alternative is true and the null is false. This is saying suppose the company was lying and understating the percent of patients suffering side effects. That means they were lying. HO is false. So this question is saying suppose HO is false all along. What type of error occurred? Well, we rejected something that was false. They were lying, and we called them out for lying. Was that an error? No, that's a correct decision. I don't need to even grab my table, because I'm pretty confident that that was the correct decision. You can confirm it, but unless I messed up royally. False, and we reject something that was false, and that's the correct decision. That's no error. All right, so that's, 4 examples of errors. It is the most confusing thing, I feel. Well, I don't feel, but everybody tells me they get stuck on the errors, particularly interpreting this. So you have to really understand what HO is saying. It's the company's claim or what it was, the default value or whatever, but definitely understand that. And definitely understand that this analysis is based on interpreting this hypothetical scenario and what it's saying about HO, whether it was true all along or whether it was false all along. Our decision is right here. You just carry that over as long as you made the correct decision based on your data. Not the correct decision based, but as long as you know how to compare your p-value to your alpha, and then you draw you grab your errors from the table if necessary. Okay, I'm going to do another example. We still have yet to do a two-tailed test, so I'm going to do one of those, and then I'm also going to do more errors, making sure we reinforce that notion. Okay, problems up on the board. Hopefully you can read it. I have to write small because I need the space. Last time I wrote too big and it was all over the place. All right, I'll read it off to you in any case, and pause it if you're actually copying this down. But the percentage of Americans that wanted to withdraw from Iraq in 2007 was 63%. So that's just information that's given. Suppose in a 2008 survey the following year, of 86 Americans, 62 wanted to withdraw. Perform a hypothesis test to determine if there is sufficient evidence at the 5% significance level that the percentage has changed. Okay, so it's again just telling you to do the whole test. It's not walking you through the steps individually, step by step, but we still want to make sure we do all the steps. We're going to start off with, and I'm not going to label it anymore, but you're going to decide if it's means or proportions. This one's proportions, obviously. Percentages of Americans that want to withdraw from Iraq at different years. Okay, so they basically said it was 63% in 2007, and they want to compare 2008 to that, so they want to see if it's changed since then. So the idea is the null is, there's no claim anymore, so it's not a claimed value, but it is, I mentioned it's also like the default value. And we default to assuming that things have not changed, everything stays the same, people's opinions on the war stays the same, consistent. nothing causes cancer, everything is cool, unless we find evidence otherwise. So we default to the percentage in 2008 is the same as it was in 2007. So this is the same as before. You don't have to label it, but I'm going to mention it so we can be clear that we're going to start with a null hypothesis and assume this, that it's the same percentage as it was the previous year. We're looking for evidence of what? Your alternative is going to have p, it's going to have 0.63 as well, as usual, the same symbol, the same parameter, and the same value. It's just a matter of whether we're doing a left tail test to see if it's under 63%, a right tail test if we think it's increased from 63% to a higher value, or, and you got to read, and this time it has changed. This is the first time we're having a not equal to. That makes it a two-tailed test. We don't care if it's gone up or gone down. We just want to see if it's different from or has changed from the 63%. At this stage, if it were an exam, I would make a note to myself, my future self. I don't know. I'm going to be doing my null, my null and alternative. I'll do my z-score here, my test statistic, and I'll do my p-value maybe up here. So I'm going to remind my future self that is a two-tailed test, because that is something I will have to worry about later, though. In the meantime, I still have to do my z statistic. It's going to be, I erased it, but I'll just assume you have it handy nearby in your notes or the formula sheet. All right, p hat. It's my sample proportion, so I have to compute it this time. 62 out of 86. And I got 721 it rounds up to. That does seem different from the 63%. Looks like it's different, but is it different enough for us to conclude that it has changed? Or are we going to attribute that to random variation? It depends on whether we reject or not reject the null. Next step. Oh no, not next step. I got to sort this out. P, the population proportion that still want to withdraw from Iraq. We assume it's 63% as it was before. Our Q is 37, and our N is 86. Okay, where am I going to do my Z? I'm going to do it up here. Meaning I'm losing my reminder, but I'll remember. Z is equal to 0.721 minus 0.63. I want to know that's a difference of 9%, so it's a 9% above what it should be. I'll mention that later, but I'm just going to note that now. Alright, I plug it all into that. As usual, type it in and try to enter that in one shot using parentheses to make sure it does the subtraction first. Parentheses 0.721 minus 0.63. Close parentheses, divide by the square root of 63 times 0.37 divided by 86. I got 1.74 and it rounds up to 8. I'm going to circle it even though it's not my final answer. My final answer is just rejecting or not rejecting. Okay, and now I'm going to do my p-value. This z statistic has a distribution that's n01. 0 is there, and my z-score that I got, my test statistic, ends up about right there at 1.748 on my standard normal curve. Now, the p-value is areas under the normal curve. If we're doing a left tail test, it's literally going to be all of this. It doesn't matter that that's a high probability and that's the bigger area. You don't always go to the tail for if this is less than. You're literally testing to see if there's evidence that it's less than. And if it's this way, you're testing to see if it's greater than. You're literally going to always be doing the right tail. So left and right tail, you're literally going in that direction in either of those cases. Now, we don't have that. We have a new situation, and so I have to kind of go through this. When you have a two-tailed test, you're looking for something as extreme in either direction. So when you get a z-score of 1.748, you need to go to that tail and then double it. So the p-value, I mentioned it back in 9.1, but I haven't done one yet. This is my first time. I want to get that tail probability. I do want to do the tail and then double it. And I have to adapt. That means if I get it, I could get a negative z-score and it could end up on that side, and I'm going to go left tail and double it. So here for two-tailed test, I have to adapt to whatever side this is, whatever side is on. All right, anyway, my p-value is going to be doing this tail probability, so I'm going to be doing, I'm leaving some space here for something. Normal CDF, 1.748, 10 to the 99, 0 and 1. But that's going to give me just this right tail, and for my p-value, it's double that. So I'm just going to multiply by 2. 2 times that. So I have to remember, that was a reminder. I erased it, but that was why. Once I know it's two-tailed, I should remind myself of that when I get to this stage, because it's easy to forget. I should remind myself at this stage I will need to remember it's a two-tailed test and to double that. Picture also helps, but again, you could easily forget you're doing a two-tailed test. Anyway, you can type this in one step on your calculator. You can do 2 times and then call the function normal CDF. I'm fine with you doing that, but for your notes I want to do them separately. So let me real quick do just this normal CDF, 1.748, 10 to the 99, 0 and 1, gives me 0.040. And then as a separate step, I'll double it. But again, you could do it in one step. Times 2 will be, that's 4%. Doubling it gives me 8%. That's my p-value. That's a probability in both tails combined, meaning it's a probability of getting something that far out from the 63 in either direction, because for you don't care which direction, you just want to know if it's deviated far enough from the 63 for you to conclude that it's changed. Alright, I'm ready for my conclusion. If I have space for it, I do. Let me write my p-val. Alpha, my p-value I just found. And the double tail probability is your p-value, the total probability. My alpha, where is it at? 5%. Going back to the usual 5%. 8% is greater than that, and therefore that's not enough evidence. Again, evidence is in the form of a small p-value, and that's not small enough. We do not reject. Which means we're not rejecting null, meaning we're kind of accepting that it stayed the same and it's still at 63%. We attribute the fact that we got a sample that has 72.1% wanting to withdraw is just pure coincidence, just the randomness of the sample that happened to get a lot of anti-war people, a slightly higher proportion of anti-war people than we would in the population. But we think it's just random, not because opinions have changed. That's what we mean when we say we do not reject the null. Okay, where am I at? Notice that if you forget to double it, you would have drawn the wrong conclusion, so be careful. Now, let me do some follow-up questions. I want to do some more errors. Let me leave my null and alternative because that is important. And the interpretation is important too. That's the same, that's different from. So the null is that it's the same as it was in 2007. And the alternative is that it's changed in 2008. Okay, let me write my error questions. Suppose there are a percentage wanting to withdraw. So there are different phrasing and you have to be able to interpret. I'm going to say remain consistent from 2007 to 2008. What type of error occurred? I'm also going to go ahead and write the next one. I'm going to do 2 of these errors as usual to talk about the different combinations of true, false, reject, not rejecting. I want to leave with my conclusion for sure, and I definitely want to be able to refer to my null hypothesis as I do this. This I won't need, so let me erase this. All right, second follow-up question. Suppose the percentage wanting to withdraw increased. In 2008, or from 2007 to 2008. What type of error occurred? All right, so once again, to determine what type of error, it's a matter of determining what these hypotheticals are saying and noting our decision. Our decision's done, it's final, we did not reject. So for both of these, we're going to be basing it on our actual decision of do not rejecting. Now in one of these situations, we made an error because it was a wrong conclusion here, and the other one, it's a correct decision. But we got to sort it out by interpreting what this supposed hypothetical is saying about HO. And HO is saying it stayed the same. It's still 63% in 2008 as it was in 2007. Let's read this. Suppose their percentage remained consistent, meaning it stayed the same. They're saying here that HO is true. What was our decision? We did not reject something that was true. Before I even look at my chart, I should be able to determine whether that was a correct decision or not if I understand the test. So it is helpful. I do want you to, as an exercise, try to figure out at least did we make the correct decision or not. True. It didn't change. We did not reject it, meaning we're kind of accepting it. We never say that, but yeah, for sorting through this, we can think of it as by not rejecting it now, we're basically assuming or accepting that it stayed 63. True, we didn't reject something that was true. That's the correct decision. That's no error. Next one, suppose a particular, okay, so what's this saying about HO? True or false? HO again, it stayed the same. Suppose a percentage wanting to withdraw increased. Now they didn't say it changed or it's different from, but increasing means it's changed or it's different from. So that counts as being different from. That's a change. So they're saying HO is false. HO is saying it stayed the same. This is saying it didn't stay the same. And so we're saying that's false. The alternative was true. But we don't deal with the alternative. We deal with the null. All right, our decision right here, do not reject. It was false. We should have rejected something that was false. But the evidence, based on our sample, led us to not reject it. That's a wrong decision. That's an error. What type of error? I don't know. I gotta look it up. False. Do not reject. Type 2. Type 2. And we're done. Okay. That's it for that. I'm not done. I have a follow-up to this and a couple of comments, but I want to do another one of these. It's going to be a lot of, well, let's see. It's going to be the same question, just wanting to withdraw from Iraq, and if opinions have changed from 2007 to 2008. It's sort of a follow-up, but it's suppose in a different sample. Of this time 232 Americans. Taken in, or surveyed in, should I say, in 2008, 125 wanted to withdraw. Question will be the same. Is there sufficient evidence at the 5% level? I'm going to abbreviate a little bit. That the percentage has changed. very similar question. Practically the same, but new data. So I'm going to fly through it a little bit. It doesn't give details, but it's referring to the same question, wanting to withdraw from Iraq. Did I say that? Yeah. Okay, so still 2007 it was 63%. Sometimes they change the type of test. Sometimes they'll ask a different question. Has increased or has decreased? No, they're still doing a two-tailed test. So it's not equal to. I'll make my reminder, I don't know, like right there maybe, two-tailed when I get to there. So I'll have to read, well, I'll still be doubling that tail probability, but we'll talk about it when we get there. But it's a reminder not to forget that I got to do a two-tailed test. All right, my p-hat is different. New sample. Last time it was 72%. In 2008, wanted to withdraw, meaning it was slightly higher than the 63%. This time, it's 0.539 when we round to 3 places. So this percentage is less than what we expected. Doesn't mean we're going to reject. It depends how far less, and depends on all the computations and probability, basically. P is 0.63 still. Q is 0.37. And N is different now. So p-hat is different, N is different at this stage. And we got to redo Z, that means. Okay, so a new p-hat, 0.539 minus the p, 0.63, divided by that square root of, still 0.63 times 0.37 divided by, my N is different, 232. I'm going to note 53%, 53.9% is like 54% almost. That's 9% below 63%. So it's about the same distance as the other one. The other one was about 9% higher than the 63. This one is 9% lower than the 63. I do want to note that for a future conversation we're going to have. But not yet. Right now we're just going to grind this out. We got negative 2.871. Okay, I'm good. Alright, I'm ready for my p-value step. I have my reminder. I'm going to have to do the two-tailed because it's not equal to or has changed. This is a z-score still. It's still on the standard normal curve. I'm going to draw a little bit bigger. Just going to point to things, and I want to note that last time, comparing everything to 63%, if you get a sample and exactly 63% want to withdraw from Iraq, that's going to be a z-score of 0. You'll get a 0 here, and your p-value will be very big, and you won't reject for sure. If you get a higher percentage, like last time we had 72.1% of our sample. That's going to be on z-score that's on this end. We had that, so we had a z-score over here. If you get a percentage of your sample that's lower, it ends up over here. Now this one is negative 2.871 is my z-score. That's much further away from center than last time. My p-value is, and so again I have to adapt. So I'm not doing left tail, I'm not doing right tail, I'm doing two tail. And if I get a z-score here like last time, I got to do the right tail and then double it. This time I got a z-score that's negative. I need to do the left tail. I'm always, for a two-tailed test, always going to that direction and then doubling. Okay, so my p-value is going to be 2 times whatever I get when I do normal CDF. I'm going negative infinity here to negative 2.871 with 0 and 1 is my parameters. Again, I could do it in one shot, but I'll keep that separate, I'll do my normal CDF first and then multiply it by 2 in the second step. Negative 10 to the 99, negative 2.871, 0.1. Oh man, what happened? Okay, I got 0.002. Is that right? Yeah. That's less than 1%. Double it, that's still less than 1%. Oops, too many zeros. 0.004. That's 0.4%. That's my p-value. And I'm ready to make my comparison. It's still 5%. So I'm comparing my p-val of 0.004, which again is less than 1%. My alpha, which is 5%, 0.5, and that's definitely smaller. We are rejecting. Okay. And so again, you have to adapt for the two-tailed test. Not only do you have to double it, you have to know how to double it. And whatever z-score you get, if you get a negative z-score, you're doing left tail and doubling it. If you get a positive z-score, you're doing right tail and doubling it. So here you have to adapt. You have to be very specific about adapting this to what sign of the z-score you got. One last thing I want to note. Yeah, just my little note. I guess I'll write it right over here. Not important other than just understanding little minor point. Note p hat of 0.721, which is our result from our first sample, with n was equal to 86, was it? Yeah, 86. And our new result, 539. With an n of 232. The p-hats. 72.1% of our first sample wanted to withdraw, and 53.9% of our second sample wanted to withdraw, are both 9.1% away from what we expected based on our null hypothesis, assuming that to be true, from the 63%. So they're both the same distance away. And at first you would think that would result in the same conclusion, because it's the same distance away, but the difference is the sample size. Being 9.1% away is stronger evidence when you have a bigger sample size. So this one was stronger evidence because as you increase the sample size, if this is true, and this percent is still 63, you increase the sample. We talked about this in chapter 7, but it's related to this as well. If you increase the sample size, it should be closer to 63. It shouldn't be too far off. So when you're 9.1% away and you only sampled 86, it's not bad. But when you're 9.1% away, the same percentage, but you sampled a bigger sample size, that's stronger evidence. So you generally get stronger evidence for larger sample sizes, which is why you want to take larger sample sizes ideally. So that's just a note that this percentage doesn't really tell you. It's a percentage relative to your standard deviation, which is determined by your sample size. So the sample size makes a difference on what is considered far enough away from 63%. All right, but anyway, that's a minor point, just a little abstract technical point. But the main thing is you can grind this out, and don't forget how to handle a two-tailed test, and be on the lookout for that. Make sure you write this out. Even if I don't make you do state the null alternative hypothesis, it's very helpful because you want to go back to that, not only for your p-value, but also for your errors. Okay, that's it for 9.2.